Jai Hind. Myself PANKAJ GAUTAM. So in the series of electromagnetic field theory, in third lecture we will discuss about electrostatics. We will discuss about what are the electric laws and boundary conditions of electrostatic fields. So first of all, in the electrostatics, what is Coulomb's law? And according to the Coulomb's law, the force between any two point charges Q1 and Q2, the force it is proportional to the line joining between the two forces, and it is directly proportional to the product of these two charges, and it is inversely proportional to the square of distance between the line joining these two forces, like that. So mathematically we can write the expression F equal to K. K is a proportionality constant. Actually F is proportional to K1 K2 divided by R square. So K1 and K2 are the Q1 Q2 are the charges at two distinct points, and R square is the square of distance between the 2 point charges. So after the proportionality constant, we put a constant K, which is known as proportionality constant. So this is the mathematical expression of Coulomb's law. So Coulomb's law states that the force acting between 2 point charges, it is directly proportional to the product of all 2 point charges, and it is inversely proportional to the square of distance between lining the joining between two charges. So in SI units, the Q1 and Q2 are the charges, and its units are in coulombs. So it represents in coulombs, and distance is represented in meters, and force in Newton. So the epsilon naught K equal to actually K equal to, it is a 1 upon 4 pi epsilon naught, and the value of epsilon naught is 8.854 into 10 to the power minus 12. This will be used for solving the numerical problems. So it is K will be the 9 into 10 to the power 9 meter per farad. So we can write this expression for the F equal to Q1 Q2 upon 4 pi epsilon naught R square. Next, this is the graphical representation of 2 point charges Q1 and Q2 are placed at the R1 and R2 distance from the origin. So there is a distance vector between Q1 and Q2 is R12, and force on Q1 is acting at F21, and force on Q2 is acting in the opposite direction, that is F12. So these two forces F1 and F12 will be the opposing forces. So that's why we will represent here F21 equal to minus F12, or we can say F12 is equal to minus of F21. Or unit direction will also be the opposite directions of each of them. So AR12 is the unit direction in the F12 direction, and AR21 is the unit vector in F21 direction. So it will also be the opposite of each other in this direction and this direction. So R12 is the distant vector between Q1 and Q2, we discussed in earlier lecture, and R1 is the distance between Q1 point to origin, and R2 is the distance between Q2 point and the origin. So this is the distance vector R12, that is a subtraction of position vectors of R2 minus R1, and this is the magnitude of distance vector R, and this is the unit vector. So we will put these values in the formula of Coulomb's law. So the Coulomb's law states that the force acting on charge Q1 due to charge Q2, it is represented as F12, that is Q1 Q2, which is a product of 2 point charges divided by 4 pi epsilon naught R square, this is the square of distance, and multiplied with unit vector, which represents the direction of this vector AR12. So we will put the value of AR12 from here to here. So we will get F12 equal to Q1 Q2 divided by 4 pi epsilon naught R12 is the magnitude divided by R, so it would be the R cube in denominator. Further, we can write this expression as F12 equal to Q1 Q2 into R2 minus R1, which is the subtraction of between 2 point vectors, and divided by 4 pi epsilon naught, and it is the magnitude of the cube of the difference between two distances. Okay, so for numerical problems, we will use these formulas. If we have more than 2 point charges, so we will put here summation n equal to 1 to k. Okay, and so we can subtract each vector from 1 to 2 and 3, and we will add all of these forces acting on the initial charges. So what is electric field intensity? If in the previous question, if the previous state of Coulomb's law, F equal to Q1 Q2 divided by 4 pi epsilon naught R square. If we divide a force by a charge Q1, so the ratio of force upon Q1 is known as electric field intensity. So the force divided by charge would remains Q2 4 pi epsilon naught R square. So this is the electric field intensity. It is the force per unit charge. Its unit is electric field is represented by force per unit charge. And in general, for numerical solving purpose, we will use this formula, which is equal to F by Q1, and remaining Q1, Q2, Q3, and so on would be used here. And we divide 4 pi epsilon naught R square unit vector AR, and in general we can write here this AR by ARQ by this segment. So this was the electric field intensity. Next, electric fields due to continuous charge distributions. We have different types of charges. It is placed in the medium. So first one is point charge. Point charge means a charge is stationary at a fixed point. That is called point charge. Second case is line charge. A charge is distributed along a straight line, that is known as line charge, and the charge density is represented by rho L. Rho L is the line charge density. Similarly, the next case is surface charge. If the charge is distributed over a surface, that it would be represented as surface charge density, and its surface charge density is rho S. Okay. Next case is if the charge is distributed throughout the volume, any volume. So the charge density is shown by volume charge density represented by rho V. So rho is the charge density, and according to the condition, rho L, rho V and rho S are your line charge density, surface charge density and volume charge density, and for fixed point charge it is just denoted by Q. So in case of all three conditions, 3 and 4 conditions, we can represent the charges formula and electric field intensity formula, which is the formula of charge and electric field intensities we have studied in the earlier slides. So in case of line charge density, the formula of charge differential charge element would be the rho L dl, and if we integrate in both sides, we get the formula of charge in case of line charge density, which is the integration of line integral of rho L dl. Similarly, in case of surface charge, in this case, we will get the dq equal to rho s into ds. This is the charge density formula. So we will get, by integrating in both sides, q is the charge in case of surface charge density, which will be the surface integral of rho s ds. And third one is in case of volume charge, the dq differential charge element is equal to the volume charge integral. So by integrating in both sides, we will get the expression of total charge by differentiating both sides over a volume charge density. So these are the three expressions for getting the total charge in cases of line charge density and surface charge distribution and the volume charge distribution. Similarly, if we have the expressions of charge distributions, we can get the electric field intensity. So the electric field intensity is the force per unit charge. Just in earlier slides I have discussed. So E would be the integration of rho L dl divided by 4 pi epsilon naught R square AR in case of line charge. So F upon P, in place of Q, we will put these expressions in case of line charge. We will put this expression of Q in case of surface charge, and we will get this. And we will put Q equal to integral of rho v dv in case of volume charge density in this expression. So we will get all three expressions of electric field intensity for solving the numerical problems. Next is electric flux density. So electric flux density can be represented by the letter psi. That is the electric flux, and the flux density can be represented by capital D. So if we integrate electric flux throughout a surface, so we will get the electric flux, how much electric flux is passed through a surface. So this is the expression of psi equal to integration of D dot ds, where vector field D is called electric flux density. So D is the electric flux density denoted in coulombs per square meter. The electric flux density is also called electric displacement, and the relation between electric flux density and electric field intensity is represented by D equal to epsilon naught E. So where the epsilon naught is the permittivity of free space. Next, we will discuss about the Gauss law or Maxwell's equation. So there is total two Maxwell equations in electric fields and two Maxwell equation in magnetic field. So in this lecture we will discuss about only two Maxwell equation of electric fields. So first Maxwell equation is expressed by the Gauss law. So Gauss law states that the total flux, electric flux passing through any closed surface is equal to the total charge enclosed by that surface. So this is the statement of Gauss law. Mathematically we can write psi equal to integration of d psi, and in previous slide I have told you that psi equal to d integration surface integral of d dot ds. So this is the total charge enclosed by q, and this is the volume charge density. That means the total charge enclosed by that surface. So mathematically we can write the total charge passing through a closed surface is equal to the total charge enclosed by that surface. So this is the surface integral of d dot ds electric flux density, and this is the total volume charge density is mathematical expression. So this is the statement in these two terms, volume charge density and surface electric flux density. So in general, if we equate it in point form, so we can say that the volume charge density is equal to the del dot D. This is the divergence of D. So we can say that this is the Maxwell's first equation which we have to derive. This is the integral form of Maxwell's first equation. This means that the surface integral of electric flux density over a surface is equal to the volume charge density of the divergence of that electric flux density. This is the integral form of Maxwell's first equation, and this is the point form of differential form. So this is the Maxwell's first equation. This states that the volume charge density is same as the divergence of electric flux density. Now we will explain what is the relation between E and V. E is the electric field intensity and V is the electric potential. So in a closed path from A to B, the VAB will be the negative of V of minus AB. So if we add this total voltage V to A and A to B, its resultant would be 0, and it is equal to E dot dl. So we will get a conclusion that the cyclic integral over a closed path E dot dl would also be 0. This means that the line integral of E along a closed path must be 0. Physically, this implies that there is no net work is done in moving a charge along a closed path in electrostatic field. This also represents that the electric field intensity is a conservative charge. Okay, so this is integral form. In point form, we can write using the Stokes theorem. Stokes theorem states that the line integral of any vector is equal to the surface integral of the curl of that vector, which is equal to 0. So by equating these two terms, so we will get the point form of this expression, which is curl of E equal to 0. This means that the vector field satisfies, it is a conservative field or irrotational. If the curl of any vector field is equal to 0, that means it is conservative or irrotational. So thus the electrostatic field is a conservative field, and this equation is the second equation of Maxwell's equation in case of static electric field. So we have to keep in mind these two Maxwell's equation for electrostatic field. First equation was psi equal to d dot ds equal to. First equation was rho v equal to del dot d equal to del dot d, and second equation was curl of E equal to 0. So coming to the next slide. So we can after getting the Maxwell's first and second equations, we can apply both these Maxwell's equations to get the boundary conditions. We have three cases for boundary conditions. First one is dielectric. In case if at boundary there is two different materials are placed, so what is the effect of electric field and electric flux density? We can calculate here. Second case is if one side is conductor and one side is dielectric, then in this case also we can calculate. And third one is if there is a one side is conductor and one side is free space, in this case also we can calculate electric field intensity and electric flux density. So that's why we used boundary conditions to get the value of electric field intensity and electric flux density above the boundary. If there are two similar materials, if there are two dissimilar materials, if there are one side is conducting and one side is free space. So we will use two Maxwell equations, E dot dl, the cyclic integral of E dot dl equal to 0, and second equation D dot ds equal to charge enclosed. So using these two Maxwell equations, we will get the expressions of these three boundary value problems. So first condition of boundary condition is if there is dielectric medium, two different values dielectric mediums are placing at around the boundary. So if we have considered this is a boundary by this curved line and this is a medium 1 which have permittivity epsilon 1, and there's in this side we have medium 2 of permittivity epsilon 2. So this place we have considered at the boundary rectangular place for applying the E dot dl equal to 0, and for this expression we have taken as cylindrical shape, very small cylindrical shape, or we can say pill box, to apply the D dot ds equal to charge enclosed. Okay. So that's why we have taken two very small shapes at the boundary of two different dielectric mediums. So here we will apply in A, B, C, D path E dot dl equal to 0. So we have taken 0 at first left hand side. So from path A to B, this is length or delta dl, delta w, and E1t. It is a tangent component of material E1 minus E1n. This is normal component of delta h by 2. So the height of vertical height has been separated in two parts, delta h by 2, delta h by 2. So positive has been taken if we are going to downwards, and negative has been taken if we are in reverse direction. So we will get 1, 2, 3, 4, 5, 6, total 6 expressions of E dot dl equal to 0. So this will get here E1 and this will be cancelled out, E2n will also be cancelled out equal to 0. So we will get final expression by considering delta h equal to 0. Means this height is as small as 0. So that's we will get the conclusion that the tangential component are two different dielectric mediums. We have the same electric field intensity at two differential components. Similarly, by applying D dot ds equal to in this cylindrical shape, so we have D equal to epsilon E expression. So if we have calculated E expression, so we can get D by epsilon naught. So D has been decomposed in tangential and normal components. So we can directly express as E1t equal to E2t. E1t can be written as D1t divided by epsilon 1, and E2t can be written as E2t upon epsilon 2t. So in this case, E1t equal to E2t, it means it does not depend upon the permittivity material. What is the medium of 1 or what is the medium of 2? It means the tangent component electric field intensity is continuous above the boundary. But here there is epsilon 1, epsilon 2. This means the electric flux density is discontinuous across the interface because there are epsilon 1 and epsilon 2. So further, we have applied E dot ds equal to charge enclosed This is also called Gaussian surface, assuming delta S tends to 0. So the charge enclosed is the differential charge delta Q, and the positive charge is entering charge has been taken and leaving charge has been taken as negative. So we can say D1S normal component delta S minus D2S normal component into delta S. So we can write D1S minus D2S equal to rho S by cancelling the small surface. So we can write here the D1N normal component of electric flux density D1 minus normal component of electric flux density D2 is equal to the surface charge density. So this is also expressed as if there is surface charge density, if there is if there is a value of charge density, then the normal component is not continuous above the boundary. But if there is no charge density, if it is a charge free region, then the D1 and normal component of both mediums electric flux density would be the same. So this is a case where there is no charge density, or we can say rho is equal to 0, and this is the case if there is charge density, then the electric flux density would be the discontinuous. It is not same. Similarly, by putting D equal to epsilon naught E, so we can derive the normal component of electric field intensity at both the mediums E1 and E2. So D1n equal to epsilon 1 E1n equal to D2n can be written as epsilon 2 E2n. So this means that the electric field intensity's normal component are discontinuous at the boundary because there are epsilon 1 and epsilon 2. Next is second case is if there is a conductor at one side and if there is a dielectric medium and second side, another side. So this is the boundary we have considered, and one side is medium 1, that is epsilon 1, and second has been taken medium 2 epsilon 2. We can consider conductor at one place and we will consider dielectric medium of second side. So same, we have taken a rectangular section of a very small height to apply the E dot dl equal to 0, and for cylindrical section we will apply D dot ds equal to charge enclosed surface integrate. Maxwell's second equation. This is Maxwell's first equation and second equation. So one by one we will apply these equations in figure 1 and figure 2. So in figure 1, in figure A, assuming that this path is a very small, we have taken A, B, C, D, A path. So the width is delta W and height is delta H. So this is the complete height delta H, which is tends to 0, and at the boundary we have divided into two parts, delta H by 2 and delta H by 2. So after applying this equation in this figure, so we have written 0 at the left hand side and E dot dl. So E dot dl in the first medium, in electric field, in a perfect continuum, electric field would be the 0. Okay, so that's why we have taken E equal to 0 here, and the width of line segment is delta W. Second, the E dot dl equal to 0, the 0 into delta H by 2. The 0 delta H by 2 is this height. So this is delta H by 2, but in case of pure perfect conductor, the value of electric field intensity will be 0. So we have taken here 0. Second, when we get in another medium, so we will get the En normal component of electric field intensity delta H by 2, and second minus tangential component of Et and delta W in permittivity in a dielectric case. So in the conductor case, E will be 0, but in dielectric case there will be E. Et will also be there and En will also be there in dielectric case. So that's why these two elements will be the 0 in case of conductor, but in case of dielectric there would be the electric field intensity, which is decomposed in normal and tangent component, minus En into delta H by 2, and this is the last case where we have getting this point E into delta H by 2. So there are total 6 expressions, 1, 2, 3, 4, 5 and 6. By joining all the 6 expressions by their direction, according to the forward direction it has been taken as positive, and for reverse direction it has taken as negative. So the negative is considered for the opposite direction and positive has considered for the same direction. After solving this, some elements will be cancelled out. So this will be the cancel out, this will be the 0. We will get Et will be the 0. So the tangential component of electric field intensity would be the 0 in case of conductor and dielectric boundary conditions. So for the second figure, this expression for this cylindrical pillbox Gaussian surface, we will apply this equation of Maxwell's d dot ds equal to 0. So we have taken the Maxwell's equation, the charge enclosed equal to the total flux passing through it, which is d dot ds equal to 0. D dot ds, integration of d dot ds equal to charge enclosed. So this is the charge passing out through the flux, which has taken positive, and this is the negative terms representing the charge leaving out that surface. So and which is equal to the charge remains inside that surface, or differential charge delta Q. So delta Q equal to dn normal component of delta S, because charge is entering here and exiting here like this. So charge is this one. Charge is entering and leaving. So leaving has been taken as negative and entering has been taken as positive. So we can write this as dn normal component of electric flux density is equal to the charge divided by that differential surface, which is equal to the charge per unit area is defined as surface charge density. So we can say that the normal component of electric flux density is equal to the surface charge density covering that surface area. In the static conditions, we can say perfect conditions. There is no electric field may exist within a perfect conductor. That means that in a perfect conductor, E would be 0. So the rho E volume charge density would also be 0. Since there is a relation between E and V, E equal to minus of divergence of gradient of E0, E equal to minus del V equal to 0. So there can be no potential difference between any two points in the conductor. Okay. So and by using this normal component, we can get the tangential component dt equal to epsilon naught dt equal to 0. The tangential component will be 0 and normal component will be the surface charge density. So this was the boundary condition in case of one side is conductor and another side is dielectric material. So the third case is if there is a conductor at one side and if there is a free space at another side. So this is the third case in which we have taken conductor at one side and free space at another side. In free space can be written as epsilon naught and conductor, in case of conductor, E equal to 0. Earlier we have discussed. So in this condition, boundary condition at interface between a conductor and free space can be obtained by replacing the relative permittivity by equal to 1. So actually epsilon is equal to epsilon naught epsilon r equal to 1. So in case of free space, the epsilon r is 1. So we can written as epsilon equal to epsilon 1, which is so it is taken as free space regarding as dielectric material. So this boundary conditions can be, in this case, this is the conductor case and this is the free space. In conductor case, there is no electric field intensity and no volume charge density. So there will be the in free space, there will be the tangent component and normal component. So the resultant electric field would be like this. And this shape has been taken that implies that the electric field must approach a conducting surface normally. This means that the electric field will approach the normal conducting surface normally. So dt is the epsilon naught et equal to 0, which we have derived in previous section in case of conductor condition. This has been taken from here. The tangent component equal to epsilon naught et equal to 0 because et will also be 0. So normal component is equal to the surface charge density considered in that surface. So these are the three boundary conditions for considering the electrostatic field. We can solve the numerical problems to calculate these values or to satisfy these boundary conditions. So this was the electrostatic field in the electromagnetic theory. Okay, thank you.